Let us start lecture 56, and the course is on phase diagrams in single component and binary systems. Today's topic it's basically evolution of phase diagrams when we consider different values of del H mix for both solid and liquid solutions. In fact, in the last class we have already started it. We have taken 4 combinations, and 2 combinations we have seen how the phase diagram appears as we go ahead with the free energy composition plots at different temperatures. And we are talking about binary solutions. Now, today also we will continue our discussion on the same topic, and today we will try to look at the third combination, where we talk about a situation when del H mix of solid solution is highly negative, whereas del H mix of liquid solution we can take it as 0, okay, and see how the phase diagram evolves. We will see that. So, what we have done, we have taken regular solution model, keeping temperature and pressure constant 1 atmosphere, and at each constant temperature we will be saying the equilibrium conditions with reference to free energy composition plot. And we are talking about a binary system. A, B are pure metals, let us say X A and X B are the mole fraction of A and B, and when we add them together it becomes 1 mole solution. Okay. So, that is the framework, and we have taken 4 conditions or combinations. So, combination 1, where we have taken omega s equal to 0, omega L equal to 0, and it corresponds to del H mix of solid equal to 0 and del H mix liquid equal to 0. Okay. Combination 2, we have taken this one to be 0, whereas this one is less than 0, and delta H mix correspondingly it will be 0 and L less than 0. And then combination 3, this one is less than 0, and whereas omega L equal to 0, and correspondingly you can write this. And the combination 4 is this one is greater than 0. This we have to take, and correspondingly if I try to look at the del H mix of solid is greater than 0 and del H mix of liquid is less than 0. So, we have done this one and we have done this too in our previous discussion, and let me just note down all those formulas what we have used. Del H mix is equal to omega X A X B, and when we try to look at solid and liquid you just have to consider for solid everything would be solid, even the compositions, and for liquid everything would be liquid, but this is the general formula. Delta G mix is equal to delta H mix minus T del S mix, and del S mix is same for both the solid and liquid solutions, which is minus R X A ln X A plus X B ln X B, and G 2 of the solution is G 1 plus delta G mix, and G 1 is nothing but X A G A naught plus X B G B naught. Fine. These are the equations what we will be using. and we will be seeing the equilibrium between two phases when we draw G2 as a function of composition. G2 versus XB, we will plot plots of solid and liquid solutions, fine, and then we will check the equilibrium conditions. So, these are the frameworks. We have done for two conditions. Combination 1, it gives me a phase diagram like this, isomorphous phase diagram, where T composition XB equal to 1, Xa equal to 1, two pure metal sides, and we will be taking the melting point of B is greater than melting point of A, and the reference free energy temperature plots for two pure metals are arbitrarily chosen like this. This is Gb naught solid, this is Gb naught liquid, and this corresponds to Tmb, and then another one, this is G A naught for solid, this is A naught for liquid, okay, and this corresponds to Tma. That was the consideration, and the plot for combination 1 look like this, where this is Tmb and this is Tma, and combination, what was that combination? Del H mix of solid equal to 0 and del H of liquid equal to 0, fine. That was the combination, and then we have liquid, we have solid, and in between we have solid plus liquid at any temperature if we consider. So, the composition in between this, okay, any composition, let us say we take X0 with reference to B, this composition will break into two solutions of solid and liquid, and their compositions would be Xb of solid and this would be Xb of liquid. So, those two phases will coexist, and the free energy diagram, free energy composition diagram would look like this. So, this is at a temperature in between Tma and Tmb. So, this is the temperature we are considering. So, at this temperature T, our free energy composition plot would look like this. This is 0 point, this is Gb naught for solid, and this is Ga naught for liquid. So, this is Gb naught solid, and these can be taken as reference value to be 0, and corresponding positioning of Ga naught solid is kept here for metal A, and for metal B it would be, this is Gb naught liquid, fine. So, this is temperature equal to T, pure B side, pure A side, and so we have taken, now we have to see a liquid G1, this is G, this one is G1 liquid, and this one is G1 solid, that straight line, okay, and corresponding free energy composition plot, this is G2 solid and this one would be G2 liquid, and the equilibrium is this one, and the common tangent, we draw a common tangent like this, and these two compositions Xb of solid and this is Xb of liquid. So, these two compositions are this and this. So, that is the correspondence of Gibbs free energy versus of the solution versus composition, and the phase diagram. Okay. So, this is G, fine, and this is the phase diagram which is called isomorphous, fine. And the second case, second combination 2, it was like this, the phase diagram looked like this. This is x b equal to 1, x a equal to 1, this is T m b, this is T m a, and we saw such kind of diagram where we have liquid stability, solid, and in between we have solid plus liquid, and here also solid plus liquid. In order to differentiate between these two solids, we have taken this one to be 1, this one to be 2, and they are of same crystal structures, fine. And if we see at this temperature, let us say this is the temperature we are talking about. This is the temperature, let us say. So, we see those 4 compositions, equilibrium compositions. This one is XBS1, this one is XB of L with in equilibrium with S1, this one is XB of N in equilibrium with XBS2. In fact, sometimes many books you will see that first composition what we are writing, after that we can write, for example, this one can be written as XB of liquid in equilibrium with S1, okay, and this one can be written as XB of solid one equilibrium with liquid. This one can be written as XB of liquid in equilibrium with S2, and this one can be written as XB of S2 phase in equilibrium with liquid. Okay. So, like that way one can actually distinguish the composition of the phase, and that composition will be in equilibrium with what phase. Okay. That way one can also identify those compositions. And here if I try to look at the free energy composition plot, so this is the temperature which is below melting point. So, 0 0, this should be solid. Please understand that this reference value is chosen as per the stability of that phase of that particular metal at that temperature. Okay. So, this stability is maximum, so we can put it as a 0 reference, and this is G A naught solid, and corresponding positioning of G A naught liquid, and here this will be G B naught liquid. Okay. So, now I will have a liquid line for the G 1, this is G 1 liquid, and this one is G 1 solid, and we saw this is at a temperature T, this temperature we are talking about, which is below melting point of A and below melting point of B, and it is chosen in such a fashion, the free energy plot would be, this would be very deep, fine, and the solid line would be like this. This is G 2 solid, and this one is G 2 liquid, and we can have common tangent on both sides. This is one common tangent, and here is one more common tangent. Okay. So, this is one composition, this is one composition, this is another, this is another. X B of solid 2, this is X B of liquid, this is X B of liquid, and this is X B of solid 1, fine. So, now we could see that between these two liquids we have liquid phase which has the lowest free energy as compared to the solid solid solution free energy. Fine. And right side of it we have only S2 which has a lower free energy compared to liquid solution. Left side of this composition solid 1 would have the lower free energy, and in between 2 this common tangent we have S2 plus liquid, those that will be stable, and here between these two common tangent we have S1 plus L, that will be the stable. So, here also we are actually having the same situation. So, here we have liquid, between these two we have S2 plus liquid, between these two we have S1 plus liquid, and left to that we have S1, right to that we have S2, and in between we have liquid. In between we have, here we have liquid. Okay. So, like that way those phase evolutions are coming up. Now, if I say, let us say I have a situation and in that combination 2 we are getting what conditions we are getting? Delta H mix solid equal to 0 and delta H mix liquid is less than 0. So, let us say this difference goes up, extends, that means the liquid delta H mix is becoming far negative as compared to solid delta H mix. So, that means why that liquid is having this particular plot, this phase diagram is actually having such kind of shape, because since the liquid delta H mix is highly negative. So, the liquid stability is increasing as compared to the solid stability. I am talking about solution. So, now if we have a situation that delta H mix S is actually 0 and delta H mix L is less than 0. So, that case I am seeing that compared to this particular case and this one, these two cases if we compare, I see the liquid stability in the second one would be far more than the first one. So, phase diagram would also have a corresponding change. So, let us say, so if I try to draw phase diagram x b this way, x b equal to 1, x b equal to 0, let us say this is T m A, this is T m B. In this case what I will see, if I try to look at that, so it will be farther down. This is case, for example, this is second, let us say this is B case, and let us say this is A case. Okay. So, these two cases if I try to, or let me put a different notations, let us say combination 2 A, combination 2 B. Okay. So, this is let us say for combination, black one is for combination 2, and combination 1 if I draw it with the green one, it will be lifted here. So, this one is case 2 A and the black one is case 2 B. And if I try to see at a particular temperature, let us say this temperature I am trying to see at this temperature T, I could see that the liquid zone, this is the liquid zone for case 2, that is extended as compared to the liquid zone in case of case A. So, this is 2 A and this is 2 B. Okay. So, I could see that the liquid stability has gone up, that is the change you will observe. So, and that actually leads to a condition called deep eutectic, shallow eutectic. So, we will see that because of these particular differences, we see one case the liquid stability goes up, one case liquid stability is still there farther below the melting points of both the metals, but that stability would be little less than the case 2b. Okay. So, I just wanted to reflect that. Now, we will be seeing combination 3. So, combination 3 says delta H mix for solid is less than 0 and delta H mix for liquid equal to 0. And here the reference temperature free energy for the pure metal is same as before. So, this is for this is TMB, GB naught solid, G naught B liquid, and this is for GA naught solid, this is G naught A liquid. Okay. And this is the temperature which is TMA. We will follow the same arbitrary situation of A and pure metal A and B, and B has higher melting point compared to A. Now, that case, if I try to see with reference to delta G mix of both the solid and liquid free energies. So, I can have a plot like this. Let me take a temperature which is far more than melting point of B. So, that means a very high temperature. So, T is greater than TMB. If I take that temperature, so that case these are 2.00 points, GB naught liquid and GA naught liquid both will have 0 reference point, and corresponding solid line would be solid points would be free energy points would be here. Okay. So, if I take that way now, so this will be my liquid G1 and let us say this one is my minus T del S mix, which will be same for solid also. So, this would be nothing but delta G mix, since delta H mix for liquid equal to 0. Okay. Now, this is also same as for liquid. Now, if I try to draw del G mix for liquid, delta G mix liquid. So, now let me draw for solid. Okay. So, let me draw for solid. So, this let us say this is my delta H mix of solid, which is negative value. Fine. Now, delta G mix for solid would be, it is just addition of these two, this one and this one. Okay. So, I can go further down. Okay. So, this is delta G mix of solid, which is nothing but delta H mix solid minus T del S mix, which is same as this quantity is same as delta G mix of liquid, since that is for ideal. Okay. Now, corresponding change in the free energy of solid and liquid. So, this is also same as G2 liquid, because G1 liquid is 0 also as per this diagram. Now, G2 solid, we have to consider G1 solid now. So, G1 solid is here, this is G1 solid. So, now I have to just take this delta G mix, we have to just add to G1 of solid. So, if we add and if we draw it with a dotted one, so the dotted line if I plot, this dotted one is nothing but G2 solid. And the only change is, if you see comparatively, G2 of liquid has convex downward shape, whereas G2 solid also has convex downward, but G2 of solid is much steeper compared to G2 of liquid. So, that will make a change as we go ahead, as we decrease the temperature, fine. But at this temperature, if I try to reflect this condition over temperature versus composition, so this is xb equal to 1, xa equal to 1, this is Tm A, this is Tm B, and we are considering a temperature far above. So, this is the temperature here, let us say this is the temperature. At that temperature everything would be liquid. Why? Because liquid free energy, this particular green line is below the dotted line, dotted black line, which reflects the G2 of solid. So, everything would be liquid over the entire region. But if we start decreasing temperature, situation would become a kind of situation would be different, and that those different situations will just now reflect over T versus composition plot. So, this is temperature and composition, this is nothing but the phase diagram. We will evolve that phase diagram. So, now let us say, let us do it for other temperatures. Okay, so, that is the reference, this is G A naught of solid, this is G naught A of liquid. We will follow the same reference, and now we will reduce the temperature. So, temperature is gradually reduced, and let us say I am taking a temperature which is Tmb is less than T1 less than T. So, the T was reflected here. So, this was the T, and now we are reducing the temperature, okay, like that way. So, now we are trying to see what is the situation. Now, at that T1, and remember one thing, even if I miss to indicate the free energy, this is free energy and xb is following this way, xb equal to 1, xb equal to 0. So, that notation please put it even if I miss that, that will be common. So, now the condition this is 0 0, this is Gb naught liquid, Ga naught liquid, and corresponding solid line Gb naught solid, and here it will be little above relative position will be here. So, now solid G1 is this one and liquid G1 is this one. So, liquid will have shallower complex downward, and solid G2 would have steeper complex downward. But as we decrease temperature, the stiffness would also reduce for both the cases. Why? Because minus T del S mix contribution will be felt less, because temperature is down. Del S mix will not change, but since it is multiplied with temperature and temperature is reducing, that contribution would be less for taking that particular G2 line, whether steeper downward or shallower downward, okay, shallow downward. G1 solid, if I plot that, G2 solid, this is G2 solid, and G1 solid, G2 liquid, it could be a situation like this. Fine. So, this is G2 liquid, and they are merging at one point. Let us say this point is x0 with reference to B, because I am considering xb is varying this way, xb equal to 1, xb equal to 0, and this is G. Now, that means if I try to take this over temperature composition plot, xb this way, xb equal to 1, xb equal to 0, and this is TMB, this is TMA. Now, we have taken a temperature which was T, where everything was liquid. Now, we are taking a temperature T1, where I am seeing that at one point I am getting, which is x0 composition. That point, free energy of liquid and free energy of solid are having same value, and that point would be here, okay, and where I can actually have a situation of solid and liquid of that composition coexisting together. Okay. Now, if I take a temperature further down, so let us say this is the temperature T2, T1. Let us say I am taking another temperature which is T2. T2. Fine. T2 is still more than TMB. Now, another plot I can have 0 0 G naught B liquid, G naught A liquid, which will be having 0, assign 0 value, and this temperature is T2 less than T1 less than T greater than TMB. Fine. So, that case this is perfectly fine. I can position GB naught solid and this will be GA naught solid, and I can draw the solid G1, this is G1 solid, and the liquid G1, this is G1 liquid. Now, if I plot, okay, this is the plot we will get. This is G2 solid and G2 liquid would be, this is G2 liquid, and I see that two tangents we can draw in order to decide the equilibrium and equilibrium phases at temperature T2. So, one tangent is at here. I can extend this, I can extend and it will touch the axis, vertical axis with composition x A equal to 1, pure metal A side, and then another tangent we can draw here. Okay, I can extend this. So, now if I extend, so it will touch the this axis. Okay, and if I extend this one, then this will touch this axis here. So here GB bar of solid equal to GB bar of liquid, and this is GB bar of solid equal to GB bar of liquid. In order to differentiate these two solids, here I can put S2, this one can be put, the left side one is S1 and this one we can put S2, and here GA bar of S2 equal to GA bar of liquid, and at this point GA bar of solid S1 equal to GA bar of liquid. Okay. So, that means equilibrium as per the chemical potential is set, and those compositions are XB of S liquid, and this one is composition of XB solid 1. This composition would be XBS2 and this one would be XB liquid. Okay. So, at T2 we can put those compositions accordingly. So, this is one composition which is XBS1, XBS2, and on the other side not S, this should be liquid. Then one more is here XBS1, and here is XBS2 and here is XB liquid. Okay. All those compositions are shown here at T2. Now, let me draw it at temperature T equal to TMB. See, if I draw it at T equal to TMB 0 0, so now this one would be GA naught, still it will be liquid, and this one would be GB naught solid as well as equal to GB naught liquid. Both will have the same free energy, and here we will have GA naught solid. Okay. So, the liquid line is still this one, this is G1 of liquid, and G1 of solid would be this one. Now, if I draw the diagram, that free energy, so this will be G2 of liquid and G1 of solid would be, this will be like this. So, now this is G2 of solid. Now, we see that at TMB we have one point which will be merging with TMB at composition pure metal B side, solid and liquid would have the same free energies, solid solution as well as liquid solution. But on the other side, A side, we have one more tangent, common tangent we can think of. So, this is one more common tangent. This side, if I extend it, it will cut this axis, this here G at this location, GB bar of S2, S1, this is S1 should be equal to GB bar of liquid, because left side compositions we have marked as S1. So, these two compositions are in equilibrium, and these two compositions will actually shift towards left as compared to T2. So, this is T equal to TMB, which is less than T2, and this composition XBS1 XBL and this is XBS1, these two compositions will shift towards left as compared to the situation at T2. Okay. Now here at this location we have a situation GA bar of liquid equal to GA bar of S1. Fine. So that means we have equilibrium, and this is G this way is G, XP is varying this way, XP equal to 1, XP equal to 0, XP equal to 1, XP equal to 0. Fine. Now at T equal to TMB, so we have 2 points. One point is here and another point is here. So this is XB of L and this is XB of S1. Okay. Now let's say I go to a temperature which is in between T3, let's say I go to T3, which is in between TMA and TMB. 0, 0. Now we will be having a change here. So solid will have the reference 0 value on the B side, and here we still have liquid to be having 0 value. We can assign that because that is the stable one on the pure side. And here liquid will move to up G not B of solid or liquid, but here still we have this point to be closer to GA not liquid, GA not solid. So now liquid line would be this one, G1 liquid, and solid G1 would be this one. Okay. Now if I draw liquid one, this is G2 liquid, and let me draw the G1. Please practice this because this diagram drawing can be little tricky. Okay. This is G2 liquid. Now G1 solid will be starting from here, steeper downward. Now this is G2 solid. Okay. So now we have a common tangent now again on the A rich side. So this will be my common tangent. This will be my common tangent. If we extend it, it will cut this particular axis here. So this point would be GB bar of solid 1 should be equal to GB bar of liquid. At this location, GA bar of solid 1 equal to GA bar of liquid. So and those two compositions are coming out to be farther towards left. XB of solid 1 and this one is XB of liquid. So it will farther to be towards left. I can shift this little bit on the right here. So this will be here, and the other point this will be here. So this composition is XPS1 and this composition is XP of L. Okay. Now I see that at T equal to T3, which is in between, this is XP equal to 1, XP equal to 0, and T is T3 is less than TMB greater than TMA. Okay. That situation, this particular free energy composition plot will look like. This is G and like this. Now we have another temperature, let us say T equal to TMA, that case 0, 0, XP equal to 1, XP equal to 0, this is G, here would be GB naught for liquid, and this is GB naught for solid, and this here GA naught for solid as well as equal to GA naught for liquid, because at melting point free energy of solid, pure solid A and pure solid B, liquid A both will be having the same free energy. Okay. Now, the liquid line would be this one and the solid line would be this for the G1. This is G1 solid, this is G1 liquid. Now, if I draw the free energy, this is G2 liquid, this is G2 solid. So, that means I see all other compositions, solid would be stable, solid solution, but at x A equal to 1, that means the pure A, solid and liquid solution would have the same free energy, and we are considering only about the pure state. So, that point would be merging here. Now, we can connect the liquid equilibrium points on the left side and right side. So, this connections, so this is one part and the liquid line on the other side is this. Okay. Now, S2 on the right side, all those locus points we can connect, this is S2, and S1 we can connect like this. Okay. So, we are getting, we can actually shift this point little bit, this particular point we can shift towards right little bit just to have a symmetry in the plot. Okay. So, we can fine. So, now we are seeing only those equilibrium compositions of those phases we have connected, and we are having a plot pattern which is like this. So, if I try to plot the temperature composition, x p is varying this way, x p equal to 1, x p equal to 0. So, this is T m B and this is T m A. The plot looks like this. So, here it is this point. So, plot is looking like this. Fine. So, this is liquid and this is solid. Now, if I go farther down, let us say I am going at temperature to this is T4, which is below T m A. The plot would be, so T m A (0, 0) T equal to T4 less than T m A. If I take that G this way, x p equal to 1 and x p equal to 0 on the other side. Here G A naught solid and this would be G A naught liquid, and for B this is G B naught liquid and this is G B naught solid. So, now we can have liquid G1 is here, solid G1 is here. Now, if I plot free energies, this is G2 solid and G1 solid would be G2 liquid would be, this is G2 liquid. Over the entire composition range, I see solid has the lower free energy over the entire composition. That means, solid would be stable over the entire compositions range, and the plot, this is temperature is going this way and composition is varying this way, and we are getting a plot like this, and in here we will have solid 1 plus liquid and here we will have solid 2 plus liquid. Those will be the stable phases in between those two eyes. So, now the only difference between a condition combination 2 and 3, in case 2 that two i's were actually downwards, and in case of combination 3 i's are actually coming upward. So, that means why? Because in this third case combination 3 we have solid enthalpy of mixing is highly negative. So, solid is stable. That means, solid would be stable beyond the melting point of both the metals. And if we have further, for example, let us say del H mix of solid is less than 0 and del H mix liquid equal to 0, we have a situation like this. Let us say this is combination 3 B and combination 3 B was like 3 A was del H mix of solid less than 0 and del H mix liquid was equal to 0. So, that was combination 3 A. So, this is the plot for combination 3 A. Now, if I try to do for combination 3 B on the same plot, I have to lift this particular point where both the i's are meeting. So, it will be like this. Fine. And if I take this is for 3 B and this one is for 3 A. Okay. So, now I see at a particular temperature, if I consider, let us say I am taking this particular temperature, okay, let us say T prime. That time if I see T prime, what was the solid stability at that temperature. So, this was the solid stability, this was the solid stability for B, and for A the stability was this much. So, this was for A, okay, combination A. So, that means I see if I reduce or if I take the del H mix for solid further down, further negative, I have solid stability will go up and solid will be stable even beyond the melting point of B. Remember, this has an implication on engineering applications. So, when we talk about developing high temperature materials which can resist creep at a higher temperature, we have some systems where the in between the pure metal side have lower melting, but in between we have a phase which has a higher melting point, and we sometimes come across one particular state called one particular situation called congruent melting. So, that congruent melting phase has a much higher temperature, and if we compare the creep behavior, so the creep happens, we consider a temperature called homologous temperature. So, that temperature is around 0.5 to 0.6 Tm melting point of that phase. Congruent phase has a much higher melting point. So, we can go further above temperature for operation temperature without deforming that particular material and or without having creep in that material. So, high temperature application, this kind of phase diagram is come across, is actually taken into consideration. Fine. So, now we see in one case combination 3 we have liquid stability, in combination 2 we have liquid stability is increasing, that means liquid would be stable far below the melting point of both the pure metals, but in case of combination 3 the solid will be stable and it far above the melting point of both the metals we have the solid phase will be stable, and the composition range would expand if we consider third case combination 3 expand if delta H mix is farther down, that means farther negative for solid. In case of combination 2 liquid del H mix is farther negative, that case the composition range of the stable liquid would also expand. Okay. So, these two have its implication on the phase diagram, and we have used them for our benefit. We will see the use of those two conditions in the later lectures. So, but at least we could see that now we have seen three combinations, combination 1 which was ideal combination, combination 2 where one was ideal, that means liquid solid was ideal, but liquid was non ideal, but it was del H mix was negative, highly negative, and combination 3, solid LH mix is highly negative, whereas liquid is behaving ideally. Okay. So, this is the combination how we can form those phases. And interestingly, you can also see the stability. The stability is coming, you can actually judge the stability by looking at which phase has the lower free energy, and that will give you the feasibility. For example, if you take this particular situation when temperature was T2, between these two we have solid to be stable. Between these two tangent point cross points, solid 2 and liquid will be stable, and the right side of it solid liquid will be stable. And left to that liquid would be stable. In between we have solid 1 plus liquid will be stable. So, like that, when in fact T2, if you see, we have same situation. Here we have liquid, here we have solid 2 plus liquid, here we have solid, here we have solid 1 plus liquid, and here we have liquid. Okay. So, it is matching. So, it is matching with the phase diagram, and gives free energy versus composition plot will be decided by the free energy hierarchy, okay, and then everything will fall in place. So, let me close our discussion today. So, we will continue our discussion. Now, we will try to look at the fourth combination, which will become little tricky, but we have done those two combinations. The fourth combination you can segregate into two parts, and two parts we have done it already. We will see that. So, till then let me close here. Thank you very much.